In the last example, we saw how badly things can go if you use FTC when your function's not continuous, where it has an asymptote somewhere in your interval. So now I want to use the geometry to see how to take these integrals, how to evaluate them, even though they have asymptotes. I still want to evaluate them, I just have to be careful when I do so. All right, so I'm going to take a simpler example. I'm going to take the area in blue here, so between the x-axis and 1 over root of x, I'm going to go from 0, which is a vertical asymptote for this function, all the way to 1. So this area is the integral from 0 to 1 of top minus bottom which is the integral from 0 to 1 of 1 over root of x minus 0. Now I'm having issues with this point. X equals 0 is a vertical asymptote for this graph, so it isn't a continuous graph at x equals 0. So I cannot use FTC. So I'm going to do something that's close to what we did in the first example when we looked at improper going to infinity, so x going to infinity. I'm going to stop before I get a problem. I'm going to stop just before I get to 0, so right here, and then I'm going to use a limit to send my hand to the asymptote. All right, so the idea I'm going to look at the same graph, and I'm going to go up to 1. I have no issues with 1, so there's no need to stop. But here, I don't want to go to the asymptote because I want to be able to use FTC. So I'm going to stop at t. So this area, which is truncated, which is a bit shorter, that I'm going to call AT. So let me compute AT first, and then I'll look at what A should be. So AT is the integral from t to 1. And notice that t is bigger than 0 here. So from t to 1, I don't have any issue. My function is continuous. I could graph it without lifting my marker. So I will be allowed to use FTC. All right, so I get x to the minus 1/2. And so that's x to the 1/2 over 1/2 from t to 1. And I get 2 times 1 minus 2 t to the 1/2. So 2 minus 2 root of t. So this formula is valid for any positive t, not 0, but I'm going to use a limit to send that red line to the black axis. So if I want the whole area, I'm going to take the limit as t goes to 0 of a of t, which is the limit as t goes to 0 of 2 minus 2 root of x, root of t, And then that's 2 minus 0, so it's 2. So I want to say that the whole area from 0 to 1 is equal to 2. The only thing that I have to be careful of here is this condition here. This is only valid for t bigger than 0 because otherwise I cannot use FTC because I still have the same vertical asymptote. And so here I need to make sure that I'm writing that my t's are positive, so I'm going to need plus and plus to say that I'm approaching 0 from the top, so I'm approaching 0 from the right. Alright, so the lesson from this example is that if I have an integral from a to b of f of x dx, and let's say that this a is a discontinuity for f of x. So that might mean that your denominator is 0, that the interior of the log is 0. So if it's a discontinuity, then instead of evaluating this, I'll replace the issue with t. So here I've replaced 0 with t, and then I can compute this. But when I want a, I need to write a limit before. So I need the limit of a, and because I want to avoid a, I'm going to be taking values on the right closer to b than a are, so I'm going to put a plus. Alright, so that's what I wanted to get from this example. In the next video, we'll have a definition of improper integrals of type 2 for problems points here, which we now know, here, which we'll see, and somewhere in between, which we'll do as well.